Okay, let's get started. We are going to be finishing up with DDL today, and that involves talking a little bit about putting together what we talked about last time with domains and integrity constraints into creating an actual table, and then touch on views before moving on into relational algebra. I had a question on Piazza about the quizzes, about the fact that we did not get to views last time. And my take on that is that I used to give these quizzes before lecture, not after. So the quizzes were designed to make sure that you had gone through the textbook readings and the lecture notes and had read them. And that's what they're still intended to do. So even if occasionally I do not get through all the material in lecture, I expect you to have looked at the textbook for that day and gone through the lecture notes and the readings. That's being well prepared for class. That's what I expect. So even if I don't get to something, I still think you should be able to answer the questions on the quiz for that day, because those quizzes were specifically designed to be answerable without the deeper knowledge that you get from lectures. So it will occasionally happen. Before you do the quizzes, definitely make sure you've tried to look at any material that I may not have covered that day. It typically is not going to be all that much, and you should be able to answer the quizzes without any difficulty. Okay, so let's dive in, and I'm not going to go back through all the different things we went through last time. We talked about how you create new data types with the create domain command, and how you are able to specify entity integrity by saying not null, how you can specify primary keys, foreign keys. You put this all these declarations together in the create table command. So it's used to specify the columns, their types, and then any entity constraints, any integrity constraints you want to place on the table. So as an example, in the Dream Homes case study, there's a property for rent table, and this is how we could declare it. So this is at the top all of the attributes that are in the property for rent relation, and the underlined attribute is its primary key. Branch number and staff number and owner number are all foreign keys. We'd like to declare this table using SQL. So we would probably want to start by ensuring that our foreign keys refer to valid tuples in the relations that they're linking to. So we create new domains for owner number, staff number, and actually there should be one for property number, branch number here as well. Just wasn't enough room on the slide for it, hence the ... But for owner number and staff number, you can see that we are ensuring that the value is in one of the either owner numbers or staff numbers from private owner and from staff. Then we create a property number that's a varchar 5. We want to ensure that the number of rooms is between 1 and 15, and we use a small int for this because that would save storage. And then here's the declaration. So we're listing at the beginning our columns and their types. So property number is a P number, and we're saying it's not null, which it must not be because it's going to be the primary key. And then we're assigning some defaults to the rooms and rent columns. And for all of these, we want to make sure that they are not null. We want to specify the number of rooms, what the rent is, whereas it could be that there is no staff number yet assigned to the property, so we're allowing it to be null. However, we have also assigned to it a constraint called staff not handling too much. We showed you that at the end of last lecture. So there was a constraint where we didn't want any staff to handle more than 100 properties. So we're now using that constraint for staff number. And then we have our primary key, which is property number, and then the first of our foreign keys, staff number, references staff, and then the two conditions, so on delete. If that staff number is deleted, we simply want to set the properties staff number to null to indicate that no realtor is currently handling it. If the staff member is updated, for example, we change their staff number, then we want to cascade it so that we update the staff number in the property for rent as well. Okay, so that's an example for the property for rent table. Questions about that? Okay. Then after you create a table, you sometimes need to alter it, most often by adding or deleting a column, by changing a data type. For example, you might have declared the rooms for rent as an integer, and then later someone comes in and realizes you could have used a small int, so they might want to change the type from an int to a small int. I've had the situation where initially I thought I would use a natural key, and later I added a column as a artificial key, and then I wanted to, in addition, add a primary key. So you can do that. So there's a whole lot of things you can do with the alter table. Typically, you just Google it. Okay, I don't encourage you to remember the details. But here's just a couple examples. In this case, we're dropping the default for the staff or for the position. So alter table staff, then alter position, drop default. So the general format is alter table, you give the table name, then alter column name and whatever you want to do. Again, it's not worth memorizing the syntax. You can always look it up. Okay, drop table allows us to remove a table from the database. It's pretty uncommon unless you're simply creating a fresh copy of relations. That's why in my hotel.sql it starts with 3 drop tables, because I just want to start the new tables from scratch. And it's again, you can say restrict or cascade for those things that depend on it. So you say restrict if any tables depend on this table, through this isn't referring to, it is referring to foreign keys in part, but it's referring to another type of relation that we'll get to down the road, where you may have, for example, phones for a branch, and the existence of the phones relation depends on the branch relation. So a branch may have some number of telephones. If you delete the branch relation, there's no reason to have the phones relation. So the restrictor cascade is more geared toward that situation. So restrict would say don't allow the deletion if there's some other tables that depend on it. You'd have to delete the phones first. Or cascade says ripple it so that if you delete the branch, you also delete the phones. Okay, and then indices, we'll get into this in a couple weeks. By putting indices on a relation, you can help the query optimizer with its decision making. So for example, you have this query where we're trying to find the salary for an employee whose last name is White. And if all we know is that it's a set of tuples and nothing more, what's the best we can do? If it's just a set of tuples and we're looking for the last name White, and let's say it's not ordered on last name, what's the best we can do as a query optimizer? Come on, you learned this in 140, probably 102. It's a linear search. Okay, so that's very inefficient. If you're out on disk accesses are expensive. Linear searches kill you. They crush you. So it helps to put additional indices on your relations that can help a query optimizer quickly locate the particular values that you're looking for. So in this case, if we put a index on the last name and that index pointed to the blocks on disk where the different last names existed, you would only have to retrieve one block from memory or from disk rather than many blocks. So indices can definitely save you time. We won't worry about them now. We'll worry about them in a couple weeks. So we won't worry about index creation just now. So that moves us on to the last major topic for the DDL, which is views. And we've already talked about them. They're virtual relations. They typically, you use them for one of three purposes. Okay, so why would you use a view? Why a view? See, there's a number of purposes. One is to restrict access to data. So not all users need to see all data in the database. Staff don't need to know what other staff members are making, whereas a manager might. So restricting access to data. Then there's more technical reasons. So to represent aggregate data. Okay, that you get through the aggregate functions. Okay, another is to store intermediate results. Sometimes you want to do a complicated query and it's easier to break it into a set of queries, and the way you do that is to store the intermediate results in a view. Because you can't use SQL variables to do it, they store only scalars. So those are the three big reasons that you're going to use a view. Okay, so the contents of a view defined as a query on one or more base relations. There's two ways that you essentially support a view, which is either you perform the defining query every time you ask the view to be displayed, or you cache the view, the results, and you then try to update the cache. So view resolution means that you perform the defining query every time the view is requested. View materialization says you cache the results of the query and then take it from cache. Which do you think is faster? I heard it down here. Where? Someone said it. Come on, speak up. View materialization. So it's definitely faster to come from cache. What do you think the problem is from coming from cache? It's faster. There's got to be a drawback. Hard to update it. If the underlying base relations change, you're going to have to be able to update it. Okay. So some terminology. There are horizontal views that restrict a user's access to selected rows. So for example, we might have a view called Manager 3 Staff. The only staff members we want the manager at branch 3 to be able to view are the employees at branch B3. So we create a view for Manager 3 that restricts the tuples that manager can see to the staff at branch 3. So that's a horizontal view. We've restricted the rows. A vertical view restricts the access to columns. For example, we might not show the salary column because that's a column that could create a lot of angst among our staff. So we might create a view here that omits the salary column while allowing staff to access the other columns. Okay, so that's a vertical view. It restricts columns. You may or may not be also restricting rows with it. Okay, so I said that one of the reasons for using an aggregate so these two, horizontal and vertical views, address the situation you're restricting access to data. Then I said you might want to use them for aggregate data. So here's one where we're keeping track of the number of properties managed by the staff at different branches. Okay, so we create view, name it. Now in parentheses, we can create custom names for the columns, and each of them matches one of the column names in the defining query. So this is called the defining query right here. So in this case, we're doing a join between the staff and the branch relations, and the staff and property for rent relations, and we're grouping by, and notice here, this is a little unusual, we're grouping by two attributes, not just one. So we're grouping both by the branch, and then within the branch, we are grouping by staff number. Now, think about this for a moment. Suppose the staff number, we've said that the staff is unique for each branch. That each staff member can belong to only one branch. So we really could have just grouped by the staff number and achieved the same result here. So why do you think I decided to group by both branch number and staff number when I could have achieved the same aggregation, the same counts by simply aggregating by staff number? What's my motivation here? There's a subtlety here that came up with this query. I could have achieved the same grouping only using a staff number because the staff don't work at more than one branch. Okay? Pardon? That's not guaranteed. I'd have to use an order by clause to make that happen. Pardon? Well, probably because I grouped by branch number, but that's not the reason. Bingo. So you can't put, notice in the select clause, the first attribute is branch number. If it was not in the group by clause, it could not be in the select clause, because if you have aggregate functions in a select clause, you cannot put other attributes into the select clause unless they appear in a group by clause. So even though I did not need to group on the branch number, I wanted to include the branch number in the view, in the result. And therefore, I included it in the group by clause so that I could also include it in the select clause. So that's a trick. You learn these things with experience. So that's kind of a workaround for the fact that you can't always get the query that you would like. Okay, here I want the query to include the branch number of the staff number of the staff member. Okay, so again, I will let you look this stuff up. The one, I'll go over the check option a little later, so we'll get to it. Okay, it is permissible to write queries on views. Number 3, okay, I said sometimes the query you want to perform is very complicated. You want to break the query into a number of steps So it's permissible to write queries on views. Useful when a view is an intermediate result. Okay, so here's one where we only care about the staff members from branch number 3. So before, we had the staff from every branch. Now, we are further restricting it to the staff from branch number 3. But we're still doing it based on our staff property count. Now, when you do this, the query optimizer has to create a query on the underlying base relation. So what it's going to do is merge this query with the defining query. So it has to put the two together to create this new defining query. So it does it in these steps. First of all, it replaces, so here's the column names I use, staff number and count. But if we go back to the defining relation, it's s dot staff number and count stars. So the first thing we do is we replace the attribute names from the view with the attribute names from the underlying base relation. That's A. So it's now select s dot staff number as staff number, count star as count. Second thing is that any view name that is in the from statement must be replaced with its base relation. So in this case, the base relations are, it was formed from a join of the staff and property for rent relations. So we replace this from right here with its two underlying base relations, hence from staff S property for rent. Then we need to combine where clauses. So this said where branch number equals B3, and in the defining one it said where staff number S dot staff number equals P dot staff number. So we chain them with an AND clause. So this is the one from the defining query. This is the one from the query on the view. And we combine them with an AND. Then we copy any group by statements from the defining query. So in this case, remember we were grouping on the branch number and staff number. And finally, from the user query, we copy anything with the ordering. And again, we are translating the view column name into the defining query name. So when we're done, we have that final query that is used to satisfy the query on the view. And that's called view resolution. Okay. So questions about how that is done? Okay, so you remember when we talked in chapter 4, there were some restrictions on views, and they carry over into SQL. So if a column in a view is based on an aggregate function, it can't be used in the where clause of a query on that view. So for example, when I created the staff property count, I created a count field, but it was created from an aggregate function, so this query is not allowed because this is trying to do count on something that was already count star, and you can't do that. This is, if you did query resolution, would result in something that looked like count star greater than 2. That's illegal. So basically, you can't do something on a query, on a view, A query on a view cannot use an operation that would be illegal when it's translated into a query on the underlying base relations. And both of these queries would be illegal if they were translated into a query on the underlying base relations, which is exactly what we just went through. So you can't, even though you might find it helpful, you can't do it like this. Okay? Does anyone remember how you go about trying to, if you want to somehow use an aggregate function in a where clause, you can't do it, but you can do it by using group by and a having clause. Okay, so that would be a way to do it, or a subquery. You could do a subquery as well, either one. Okay, so when you have a group view, that is a view with an aggregate function, you can't join it with another base table or view. So basically, once you've created a view that has a grouped column, you can't use that in a join. So that's an unfortunate restriction, but there you have it. Okay. So then, those are the two big restrictions. Then, view updatability. So you would like, obviously, that any updates from the base relation appear in a view, and they do. But what about the converse? What about updating a view and having it update the base relations? Well, in order for that to happen, it must be possible when you insert a tuple into the view to be able to trace that back to some kind of insertion into the underlying base relations. So here's an example. It's staff property count. Let's say we wanted to insert a record showing that SG5, staff SG5 manages 2 properties. So we insert that into staff property count. That's fine. Okay, not a problem. But how does that, can we then update the underlying relations? That is, can we update the property for rent relation? No. Based on this information, what's missing if we want to update the property for rent relation? I have the answer for you, but I want an expansion. What's the issue? What information is missing?
Which properties?
So, right, which properties? Which is street addresses? What's the rent? What's the rooms for rent? Who's the owner? We don't have any of that information. So it doesn't make sense to allow this tuple to be inserted into the view because it's impossible to propagate that update back into the underlying base relation. So we're not going to allow it. Okay. Here's an example of another. Let's say we change the definition of the view and replace the count with the actual property numbers. So now this is our view, and all we're doing is we're keeping track of all the property numbers that our staff manages, and now we try to insert a specific property number. It's still no good because we still don't know the particulars of this property. We still don't know who owns it, what it rents for, the number of rooms, anything else. So we still can't allow this view to be updated. Okay, so that's some concrete examples. And these are the specific things that will prohibit you, well, that actually allow you to update. So you can't put distinct into the defining query. Okay? Because if you put distinct in, it eliminated duplicates, which means that if you insert a tuple into the view, it's possible that that tuple should spawn duplicates in the underlying base relation, but you don't know whether it will or not. Every element in the select list is a column name. So what that really means is no aggregate. This means no aggregate functions. Because if you have an aggregate function, you can't trace that back into a, like I just showed you, if you have an aggregate of the count of the number of properties managed by a realtor, and you try to insert 2 for a certain staff member, there's no way to fill in the details of those properties in the underlying relation. So anytime you aggregate something and then you try to insert a tuple based on that aggregation function, you can't disaggregate. Okay, as another example, if the column appeared as salary divided by 12, again, you can't insert a new tuple into there. And you might say that's stupid. It's easy to multiply by 12. Okay, so if I inserted 1,000, you might say, well, why can't it just replace 1,000 with 12,000 in the base relation? Anyone want to take a guess at that? Why they don't allow it? Seems simple. Think about it. Is it really simple? That might be. What if it's a more complicated expression? Do you really want to build in a symbolic algebraic solver into your database? I mean, people pay thousands of dollars for packages like MATLAB to do that. It's not trivial to create algebraic solvers. Okay, yeah, that's easy. But I could create much more complicated expressions that are very difficult to invert, which is what you have to do. So they're disallowed because no one wants to create an algebraic solver. It's too expensive and time-consuming. So it's just banned. So it's just straight column names. Okay? You're only allowed one table. No joins, no unions, intersections, or the like. You get one table. And finally, you can't violate integrity constraints of the base table. So if I try to enter a staff member and it has a salary of $150,000, and the base table says no salaries greater than $100,000, that would be a violation on the base table. So those are the restrictions placed on it. And no group by or having clause, basically the same problem that you get with aggregation. So group by is specifically there to group a set of records into a single record. So you can't easily disaggregate if you insert a new record into the view. Okay. So another term that comes up is migrating rows, which is rows that come into or exit from a view because they either now satisfy the where query or they no longer do. So for example, I have a property for rent, a view that lists all properties that rent for more than $400. So a view where properties, view of all properties whose rent is greater than or equal to $400. Well, suppose I have a property, PG8, and it's in there, it's got a rent of $450. It's not been renting. So the owner slashes the rent to $399. What should happen to that row in the view? Charles?
It leaves.
It leaves. So it migrates out. Similarly, I might have some property that rents for $385, and I decide to bump up the rent to $400. Well, that should migrate in. So when the tuples in the underlying view are updated, they may migrate in or out of a view, hence the term migrating rows. Okay? Now, migrating, this isn't really a continuation. You may remember way back when you create a view, you can have this thing called with check option. What it's doing is it's saying that when you try to insert into a view, it actually checks it, and if it would violate the underlying where condition, it won't be allowed into the view. And if you don't have it, then it would be allowed into the view, which is obviously bad because you really have violated an integrity constraint. So basically, you should always create views with the check option because you never want to allow someone to put a tuple into a view that would violate an integrity constraint in the underlying base relation. I'm not going to go over the advantages and disadvantages of views. We've already done that. The last thing I'm going to talk about, and this is view materialization. So that's where we cache a view. Obviously fast, but it's interesting as a research problem because when we update tuples in the underlying base relations, we have to update the cache. And we want to do as little work as possible. So here's our view that we're going to consider. We are selecting staff numbers from property for rent. So we want all staff who are managing properties where the rent is greater than 400. We don't care how many properties they manage as long as there's one property greater than 400. So here's some scenarios. Okay, so if we insert a row into the property for rent and its rent is less than 400, that's the golden case because we don't have to do anything. It doesn't belong in the view. Okay, so let's say we insert a row for property PG24 at branch B03. So we're going to insert PG24 for staff number SG19 and a rent of 550. So in this case, what should happen? Should a record for SG19 be inserted into this view? Jaja, should it or not? I'm inserting a record for that property. Okay, why not? Okay, let's make, good question. We're going to make the branch number be B003. So this is the property, this is the staff number, this is the rent. It will be. So we have to add it to the view in this case. Okay? Let's say we delete a record. Let's say at B003, we had a property PG22 for SG37, and we delete this record from the view. I'm sorry, not from the view, from the underlying relation. Do we need to remove SG37 from the view? I'm seeing a couple nodding heads. Why do you think so? It's good. Okay, we took it out of the base table. But there's an issue.
What if they have other properties?
What if they have other properties? They might have multiple properties greater than 400. So we don't know in that case. So in that case, you're going to basically have to dig back into the relation specifically for staff member SG37 and redo the query just for that staff member and see whether the count is still one or more. If it is, you keep the staff member in the relation, otherwise you delete it. So this is a more difficult case. Okay, so here and here, these two, they require a query on that employee or on that staff number in order to determine, in order to update the view. So you don't have to update the entire, you don't have to look at all employees, but in that case you do have to run a query on that particular staff number to know whether that staff person remains in the relation or not. So it's an interesting question, plenty of research done on it to optimize the updating of these cached views. Okay. And then there's some things we won't discuss. There's this notion of transactions in the database. So sometimes you do multiple things during an update, like a customer orders something from Amazon. It's in a shopping cart. There's 5 different items. They go to checkout. You want to update 5 different inventory items in the database. And you only want the transaction to go through if all 5 can be updated. If one of them fails for some reason, it would leave the database in an inconsistent state. So a transaction is where you have a group of queries, all of which must succeed, or else you want to be able to roll back. And it's, again, quite interesting how you do it, but it's beyond the scope of this course. Then there's access privileges. So certain users might have read-only views. Some users might have update but not delete privileges. Others might have both update and delete privileges. Again, we won't discuss that. So questions about DDL. Okay, so you should be able to actually do homework 2 now. I know that homework 1 is actually not due until tomorrow morning, but you can get started on homework 2. Okay, now take a deep breath, because we're going to start on what is probably the thing that gives the most fits during the entire semester. And this is where the 1 week where 311 comes into play, where it's good to have some knowledge of discrete math. So, Chapter 4, we considered the structure of a database, which forms the foundation for the DDL. And in Chapter 5, they talk about the relational algebra and calculus, which forms the basis for the DML, or query language, of SQL. And actually, for the query language for a relational database. And SQL is based actually on the relational calculus. Okay? It's not based on the relational algebra, it's based on the relational calculus. Okay, so going to quickly talk about what relational completeness means. Then we're going to talk about how to form queries in relational algebra and how to form queries in what we call the tuple relational calculus, which is what SQL is based on. And though the calculus is going to likely give you the heebie-jeebies, it's not as bad as it might seem, because you can often first figure out how to write the SQL query as an intermediate step and then translate it into the relational calculus if you need to. So both the relational algebra and relational calculus are formal languages. When it was first developed, it was actually developed using the relational calculus. So that is considered the language that everything must be compared with. So if you develop a language for a relational database, we say it needs to be relationally complete, which means that for every query that you can write in that language, there must be a comparable query in the relational calculus. And if it is, then it's considered relationally complete. So the relational algebra is a relationally complete language. And informally, the relational algebra is a high-level procedural language, whereas the relational calculus is a declarative language. That's why SQL is based on the relational calculus, because declarative, does anyone know what declarative, the advantage of declarative is versus procedural? So declarative means you specify what, but not how. So it means you specify what you want, but not how to satisfy the query. So the relational algebra essentially provides a high-level procedure that tells the query optimizer how to satisfy the query. So it says not only what you want, but how to do it. What set of operations to perform to do the query. The relational calculus is higher level. It doesn't specify how to satisfy the query. It just says, this is what I want. Okay? And we'll see that later when we get to it. So we'll start with the relational calculus because paradoxically, you're more familiar with procedural languages, so you'll find this a little easier because you like to specify exactly how something should be done, and the relational algebra lets you do it. So some important theoretical properties is that an operation, the relational algebra says that an operation does not modify the original relations. Instead, it creates a copy, it creates a new relation. So if you have C equals A op B, there's no modification to either A or B. C is an entirely new relation. Okay, so that's what the first bullet point says. The second bullet point says that any operation involving a relation will itself yield a relation. So it's closed. We say that the set of operations is closed because any operation we perform on two relations will yield a third relation. As an example of non-closure, let's say you have positive integers and subtraction. So do you think that that particular system is closed under subtraction? Jay, I'll let you take a crack at it. Are the set of positive integers closed under subtraction? No, why not?
Because you can't subtract a larger integer from small integer.
Correct. So I could do, for example, 3 minus 7, and the result is minus 4. That result is not a positive integer. Therefore, positive integers are not closed under the operation of subtraction. So with relational algebra, any operation we perform on a relation will itself yield a relation. So it is closed.
You can fix that.
Yes, you could. Okay. Well, we pointed out SQL does not strictly support closure because it allows a result to have duplicate tuples in it. So strictly speaking, SQL does not support closure. Okay, so 5 basic operations in relational algebra and 3 shall we call syntactic sugar operations that are provided, but they can be expressed in terms of the 5 base ones. So select and project. The very first day we talked about SQL, talked about select and project. Select selects horizontally from a relation, so it selects rows. Projection, it verticalizes. It selects specific columns from a relation. Cartesian product and select turn out to be the basis for a join. So you don't see in that group of 5 join. You see it down here as an ancillary or courtesy operation. That's because a join, as we'll see, can be done through a Cartesian product and a selection. Then there's union and set difference. And then there's intersection, which can be expressed using set difference. You'll see it. And an operation called division that also can be done through set difference. And we'll show you as we get to it how you can do that. But the 5 basic operations, select, project, Cartesian product, union, set difference, strictly speaking, join, intersection, and division are courtesy operations. Okay, so this shows you pictorially what each of them is. You should have a pretty good idea from 311. So set difference, you may have to be refreshed. It's everything in R that is not in S. So here, this is everything in R. This is everything in S. Therefore, this right here is everything in R that is not in S. So as an example of set difference, I might say I might have 2 relations, administrators and professors. And I might wish to know which administrators are not professors. That's set difference. So administrators minus professors equal administrators who are not professors. Okay, a join we've already gone over, and we'll go over semi-joins when we get to them. Division is the one that's the hardest operation to get your head around, but it's easiest to do it through some examples. So let's say that I have a database of national park visits. So I have one relation which is national parks. So maybe it has Yellowstone, Great Smoky Mountains, Glacier, blah, blah, blah. And then I have visits. So it might have Yellowstone, BVZ, Glacier, Smiley, so on and so forth. And what I want to know is I want a query that says list all visitors who have visited all national parks. Turns out that division is the operation you want. Or list all guests who have stayed at all rooms in the Grand Sylvester Hotel. So every room in the Grand Sylvester Hotel. That is set division. So in its algebraic form, you have 2 relations, R and S. And S has a set of attributes. So we call these A attributes and these B. S just has the B attributes. So S is a subset of R. So in this case, the national parks was a subset of visits. And when we do the division, what we end up with is the set of attributes in A from R. So in that case, it's the set of visitors. And in order for a tuple to appear in the final solution, it has to match all rows in S. That's why, for example, I said all visitors, list visitors who have visited all national parks. So it would only print out a visitor who had been to every national park. So for example, here we have our relation V, and here's W. So you can see that A has both 1 and 2. So A appears in the result. B has both 1 and 2. So B appears in the result. C has only 1. It has not, quote, visited all national parks, and therefore does not appear in the result. Okay, so that's what we call the remainder. In this case, C1 is the remainder, because C1 has not yet visited all national parks. So that is set intersection. Okay? I'm going to blow through the next few slides fairly quickly because it's just syntax, and you should be able to very quickly work out syntax. So the selection operator is denoted using this, I think it's a sigma, and a predicate, that is a subscript, and then the name of the relation. So for example, we're saying here, I want all staff whose salary is greater than 10,000. And anything that you have seen in a where predicate is basically valid here. So anything you have seen in a where predicate is valid here. In fact, you could have more stuff. So you could certainly imagine, for those of you familiar with regular expressions, being allowed to have a predicate that involves regular expressions. But it's just any valid, basically, the operations are Boolean operators, relational operators, and then what appears on the right-hand side could be strings, it could be regular expressions, etc. Okay, projection uses a capital Pi, and then in subscript a set of columns that you want. So for example, here we want to list the staff number, first name, last name, and salary from staff. Okay, pretty simple. And then you can combine them, so you might have that salary less than 10,000. Actually, you would do it the other way. Let's say I want it, you could say salary less than 10,000. And then you would apply the projection to that. And that's why we say it's a procedural language, because the operations are performed inside out. First the selection would be performed, then the projection would be performed. So the operations are inside out, which is just what you would expect from normal math, right? The most deeply nested ones get evaluated first. So that's why we say the relational algebra is a procedural language, because the order, you specify the order the operation should be performed in. Okay, union, pretty easy. You just combine tuples from R and S, but there's an important concept called union compatibility. Okay, it doesn't really make sense to do a union on a disjoint set of attributes. So if I have, for example, let's say pets with like name and say breed, and I have homes with address and city, it makes no sense to take the union of those two relations, right? I mean, there's no commonality. So we say that R and S have to have the same set of named attributes. So for example, it does make sense to have a union of our branch and property for rent relations as long as we do a projection on city, because we could say we want a list all cities where there is either a branch office or a property for rent. So what we do is we narrow each relation to simply city. That makes it union compatible because now they're the same named attribute, and it makes sense to do a union. It doesn't make sense to do a union on the full relations because they refer to different things. So you have to narrow it down to the common attributes. Common attributes in this case are city and city. Okay, and of course you shouldn't do silly unions. So where I had pets, I could certainly do a union of pets with veterinarians, right? Project both on the name. But that's pretty silly. It doesn't really say anything when I have a union of pets and vets. So even when you narrow it, don't do silly unions. Okay, set difference. Same thing, it's a relation consisting of tuples that are in R but not in S, and again, they have to be union compatible. They have to be the same named set of attributes. Okay, so list all cities where there is a branch office but no properties for rent. We might want to close that branch. Underachieving branch, no? Unless we enjoy paying our staff to do nothing. So this is an example of set difference and using the projection to make them union compatible. It would not make sense to say branch minus property for rent because they don't have a common set of attributes. It's only after the projection that you can perform it. Now we come to our first derived operation, our first courtesy operation. So this is a courtesy operation because it can be derived using set difference. So I think we're all familiar with intersection. Again, needs to be union compatible. So for example, we might want all people who are both administrators and professors. We would take an intersection of the two. Okay, so we can express intersection as two set differences. So we first find what is in R but not S. So this right here is what is in R and not S. Okay, so let's say that R was professors. So we'll say Brad's a professor, and Sue is a professor, and Joe and Mike are professors, and Sarah is an administrator, Nancy is an administrator. So we have Sarah, and so we're saying Joe, Mike, Sarah, and Nancy are all administrators. Brad, Sue, Joe, and Mike are professors. So the first operation is saying, let's just find the set of people who are only professors. That's the first one. Okay? Now we are saying, okay, these are professors. These are not professors. I'm sorry, this is wrong. These are professors plus admit. Jeez, go back. These are professors. These are not administrators. So when we're done, what we get is the set of professors get this right. Professors, that's right. The set of professors who are administrators. So that's how you can do intersection with two set differences. Okay? Now, we've done it turns out that MySQL does not support not all dialects of MySQL support set difference and set intersection. So it turns out there are clever ways you can get it without having the explicit operator. So for set difference, we can select, we basically have here's P, here's Q. Okay, so here is P minus Q. Okay, so we can say select star from P, so we go through each row in P, where P dot ID is not in select this set from Q. So we're saying that it appears in the solution if it does not appear in Q. So that's a way to do set difference using a table query, subquery. Or you can also do it using a left join. Okay, so you can do a left join, which means that anything that is in P but not Q will show up. So anything here in red shows up with a null from Q, whereas anything where there's an intersection will show up with something from P and something from Q. So that's what the left join does. And then you say where Q.ID is null, it will then collect everything that is null and hence contains P but not Q. So either of those two queries will yield a set difference in SQL. Okay, I don't have this in the notes, so you might want to be writing it down if you're just looking at it. Or you may want to recreate it from memory when I give it on an exam or on a quiz, which I don't think you want to do. Okay, so set intersection is also not an operation that is frequently supported, but you can get at it with a join. So let's say that you want to do an intersection of RAB with SAB. Then if you simply do a join on those two attributes and select distinct, you will end up with the intersection of the two sets, because it will only select tuples where those two sets of attributes are the same. Okay, and if nulls are an issue, typically they wouldn't be, but if they are, then you can use the spaceship operator, because it looks like a flying spaceship, to compare them. And that will return either tuples where the values match or where both A's are null, then there's still a match. So if both, there was a null here and there was a null here, then they would match using the spaceship operator. So that's a way to do set intersection using joins. Okay, we'll stop here today. We will pick it up with Cartesian products and joins on Tuesday. On Tuesday, we're also going to get into the relational calculus. So again, read through the notes. In fact,